I have just explained where an electrical double layer comes from, and now we're going to look like how an electrical double layer can give rise to an electroosmotic flow. First of all, I want to also tell you that the electrical double layer, this charged layer close to a surface, it will depend on the pH and on the salinity of the liquid, but it is also, typically it's going to be somewhere in the range 0.1 nanometer to 100 nanometer. That is a typical range that you will find. So 10 nanometer would be a typical size of an EDL. It's very little, but it's enough to give rise to a number of very important effects. So, well, another thing that I also should say, actually, the EDL, what it actually is, this typical 10 nanometer layer, it is the shielding also. This is also the shielding layer for any charge. Yeah. So basically, if I have a charge, so consider now, for example, a charge here in the liquid, any positive, for example, charge, will draw close to it a number of negative charges. And so that these negative charges, really the field lines going from this positive charge, will be shielded off by these negative charges. And so if I am a ion, a positive or negative in a liquid, I will electrostatically see that positive. If I'm a positive, another positive charge here, I will see this ion here because I'm repulsed by it. Or if I'm negative ion, I will see because I'm attracted to it. But how far can I look in a liquid electrostatically? Well, I can only see whatever is not shielded, you know. If I have a lot of negative charges around this one here, it will shield off the positive, and I will not be able to feel that attraction or repulsion anymore because all the electrostatic field lines are already absorbed by the negative cloud of ions that will form around the positive charge. So I can say the EDL, actually, that is the distance that I can see electrostatically within a liquid. Yeah? So only things that are closer than the EDL distance, than the 10 nanometer, I will be able to see in an electrolyte. Anything electrostatically that happens further away than 10 nanometer, I will not be influenced by it. So we see that the EDL, it occurs when you put a solid in a liquid. It occurs at the wall, but actually, it is an effect that is. So the shielding, the electrostatic shielding it gives, is an effect that is only dependent on the liquid properties, not on those of the solid. So that was a side remark. So now let's see what we can do with such an electroosmotic. With such an EDL in a microfluidic channel. And in a channel, I not have only one wall. Typically, I have two walls. So I'll have another wall, most likely in the same material. So I get my negative charges here, and I get a charge buildup. I will also get something that looks like here, a potential that builds up, and I have another EDL here that will be just as large. And now I will see that in this region here, I have a net positive charge, and in this region, I also have a net positive charge. Yeah? And here in the bulk, so this is the bulk, this is neutral. There is no net positive or negative charge, or all the positive and negative, they cancel out each other, typically. So now I have that in every, if I just take, for example, a cup, this is my coffee cup, if I fill it with water, I will create such an EDL, and I will have a tiny layer at the edge of the cup that is, in this case, maybe positively charged, as here. Yeah? And what can I do with that? Now I can create an electroosmotic flow. What is that? Well, if these are now the walls of my system coming towards you, I'm in the microfluidic channel. And now I have a layer of liquid here and a layer of liquid there that are positively charged. If I now put a potential difference out of the plane, so an electric field out of the plane, and I'm positive charges here, these positive layers will start flowing along the electrostatic field and will travel towards you. Huh? Understand that? Because this is a liquid layer that has a net positive charge. I put an electric field that is in the same direction as the channel walls. Or tangential to the channel walls, I will drag along this layer and it will start moving according to the electrostatic field. And this is what I call electroosmotic flow. So as this happens, I have now shown how this moves out of plane. I could also take the other picture and say, like, I'm going to move an electrostatic field in this direction. So now I'm going to put an electrostatic field in this direction, would be the same. And then I will see that this layer here starts moving in this direction, and also this layer starts moving in this direction. There will be a flow. And how does this flow look like? Well, this layer moves. I have mainly charges very close here, so I'll get a large, so I now will draw the flow lines. So this is the flow Q. No, the flow is here. Q. I will see I have our velocity, that's even better, the flow velocity U. I will have a large force here because I have a lot of ion density close to the wall. So I have a large flow here and a lower flow here. So I get something that looks like this as a flow profile, as a velocity profile. Although at the wall, again, I have this no slip condition. The liquid at the wall must be zero because it's in contact with the wall. So I get something that looks like a flow profile that looks like this. And here, of course, I have the same kind of flow profile that looks like this. So I apply my electric field and my wall starts moving, and the velocity is really, I have a velocity field that looks like this, very close to the wall. So this is a layer of typically 10 nanometer that starts moving. If I'm now a liquid particle and I'm sitting here in this position here, what I see is that my neighbor here, there's a liquid, a tiny rim of liquid just at the edge that starts moving, and I see that my neighbor start moving, and I will be dragged along. Yeah, so there will be drag force by this due to viscosity. You know, there's this viscous drag force that will start dragging along the liquid layers that are in direct here. There's a liquid layer outside the EDL, but very close to the EDL, and it feels that this, you know, there's a drag force pulling this layer, so this will be dragged along, and this starts also flowing along. So I have my red curve, and then I have this start falling, and then this one sees this one moving, this starts falling, and then this. So I see one by one my fluid layers start being dragged along according with my with the flow that is just happening in the EDL. And so I see that after a very short time, instead of having a flow profile that looks only like this, I will have a flow profile that looks like as follows. Again, here this is velocity U. So I have this flow profile, and here now these layers being dragged along, so I see it will be totally flat. Here I have the same flow profile, of course, so here at the wall it looks the same, but due to drag, these layers that are here that first were standing still will be dragged along, and they will start flowing at exactly the same speed as this layer. So after a while, first I get something that looks like this, and a bit later it looks like this, and within, say, I don't know, a few tens of milliseconds or even faster, I will have a flow profile that looks like this. That means that very close to the wall I have a certain velocity, but almost in my entire channel I will have a velocity U, a final velocity U, that is independent of the position. You see, this is a flat flow profile. No matter where I am in my channel, I will have more or less the same velocity profile U. And this is what is called electroosmotic flow.